Hi.
Let's wait a couple more minutes and then we get going.
Sounds good.
Okay, let's get started. Welcome everyone to the AQT colloquium. It is my pleasure to introduce Dr. Marina Radulaski. She's an assistant professor of electrical and computer engineering at UC Davis. She leads there the quantum nanophotonics lab. And in her short career, she's already had quite a number of different awards: Google Research Scholar of the Year 2022, NSF Career Award, one quantum leading female scientist in 2021, and a few others. So we're very happy to have her, and she's going to talk to us about quantum circuit mapping of open quantum systems in cavity QED. The floor is yours. It's your show.
Thank you, David. Thanks for the invitation. It's great to be here. Let me share my screen and get going. All right. Hi, everyone. My name is Marina Radulaski, and I lead the Quantum Nanophotonics Lab at UC Davis. While my work is mainly experimental, we also study how our hardware behaves. We model our James-Cummings and Tavis-Cummings models, which I will discuss today. And most recently, we've been thinking how we can use NISQ hardware to model these effects more efficiently. Now, I will first give you motivation from our experimental work, why we care about these specific Hamiltonians, and then I will move to their mapping onto quantum circuits and execution on NISQ hardware. So when it comes to quantum information technologies, we care about a broad range of applications, from the quantum internet, different types of all-photonic quantum simulators, and all measurement-based quantum computing, as well as quantum sensing, which has been quite popular with color centers. Now, quantum optics has an advantage in all of these fields, that it has an inherent flying qubit. And so it brings quite a unique perspective and unique functionality to all of these devices. Now, if we want to bring these devices on chip in a scalable way, we need to work with quantum emitters. Quantum emitters are just quantum, or basically quasi-atoms in solid state. Historically, our fields worked a lot with quantum dots, which have been used to demonstrate a lot of important effects in interaction of quantum emitters and cavities or other photonic devices, which are applicable to quantum communication, quantum computing, and other applications. The good thing about quantum dots was that the dipole momentum was high and the coupling to photonic devices is quite strong. However, some of the challenges which are still being worked on is that inhomogeneous broadening among the quantum dots is pretty high, so it's hard to scale up. And also the spin coherence time is short, which for some of the entanglement schemes is a little bit limiting. Then about now 20 years ago, people started working on color centers in silicon carbide and diamond, and that is the platform that we also focus on. The good thing about color centers is they're much more uniform, and they have seconds long coherence time. However, a drawback is that their coupling to the photonic devices is a little bit weaker, so we need to come up with tricks to overcome that, as I will discuss today. And before moving on to those details, I would like to also mention that there is an emerging family of emitters, and those are the emitters in 2D materials that we are also checking occasionally to see if they would give us desired cavity QED effects. But at the moment, our experimental bets are with the color centers in bulk. Now, these color centers in silicon carbide and diamond, because of all of these great properties, such as long spin coherence time, spin photon entanglement, photon entanglement in cluster state generation, single photon generation, are very well suitable to build out the backbone of all different types of quantum technologies, from communications, computing, simulations, and sensing. And most of these properties are boosted or have better fidelity or better efficiency when color centers are integrated with photonic devices. And here we differentiate between the passive photonics and active photonics. So in passive photonics, we just collect more light or couple the light from a color center into desired optical mode. And in the active photonic devices, we change the way that emitters emit. We change the state or hybridize the function, the wave function, to be not just light or just matter, but a hybridized version of light and matter. And here are examples of photonic devices that we've been making in silicon carbide and diamond. On the left-hand side, you can see different silicon carbide devices from the passive pillars that help us collect more light into the objective, to the waveguides that help us collect light into the optical mode. We're also now exploring how we can then integrate them with the single photon detectors and have the whole process on chip. To the active devices, such as these photonic crystal cavities, which resonate light at very small mode volumes and therefore interact highly with color centers embedded with them. On the right-hand side, you can see more of diamond devices, where passive devices such as grading couplers were designed using inverse design algorithms, as well as the active devices such as the microdisc and microring resonators and photonic crystal resonators, which provide us this stronger light and matter interaction. Now, our goal here is to make cavities with low loss and small mode volume so that we can study interesting cavity quantum electrodynamics. And before I get into that, let me explain a little bit of physics that's taking place here. So we usually have a photonic crystal cavity with an emitter embedded in it. The cavity it decays at a rate kappa, so that is the measure of the loss. The loss is smaller if the fabrication and design of device are better. But with silicon carbide and diamond, fabrication is quite challenging. So our kappas are more significant than in some other platforms. Dipole decay rate gamma, or rather the emission rate of our color center, is usually the lowest rate in the whole system. So in some Hamiltonians, we can even drop it. The interaction between the emitter and the cavity is characterized by the coupling strength G, which is what we want to boost to study all of the interesting physics in the system, and also for applications in quantum hardware. This rate is inversely proportional to the square root of the mode volume of the device, which is why we want to make very tiny devices, and which is why we work at the nanoscale. Now, the regime we're interested in is the strong coupling regime of cavity quantum electrodynamics, in which G is stronger than kappa quarter. Also, it needs to be stronger than gamma quarter, but that's usually the case. So the challenge here is to make small enough and nice enough or a device with fine walls that has very low losses so that the coupling rate can overcome the losses. Now, what happens when we are in the strong coupling regime? I will illustrate that on a literature example of cavity with a quantum dot. So here, we're looking into the transmission through the cavity. And so here we have the wavelength of the system, and the temperature is being scanned, which changes the frequency of cavity resonance as well as the emission of the quantum dot. And so what you see here is a typical anti-crossing pattern, meaning that two systems are interacting. So let's see what these lines are for. The cavity, if it were independent of the quantum dot, it would just be this straight line here, while the quantum dot would be this other straight line here. But because of their anti-crossing and the resonance, when they have the same energy, the energy level split by 2 times G. So here the interaction rate defines how much hybridization of the wave function we're going to see. And so what we have here is that a wave function becomes the so-called polariton, which is a superposition of light and matter. This means that the state of the system is quantum hybridized to be part photon in the cavity, which is the phase of light, and the excited emitter, which is the phase of matter. And what these systems look like, if we look into the transmission, we will see 2 polariton peaks, which are the superposition of light and matter, split by 2 times G. And this model is described by the Tavis-Cummings model, which is 1 emitter in 1 cavity. Now, if our coupling rate G is not high enough to get us into the strong coupling regime to overcome kappa over 4, a trick we can play is to add multiple emitters into the cavity. And now this is not the Tavis-Cummings model anymore, it's called the Tavis-Cummings model. And what happens here is that the light and matter interaction scales with the square root of n, where n is the number of emitters in the system. So these polariton peaks are going to be split by 2g square root of n. And so now our condition is relieved, and we can look to have g square root of n rather than g be larger than the kappa quarter. And so with color centers, we rely on being able in future to build this Tavis-Cummings model experimentally to enjoy all of the interesting physics of polaritons. What that is quantum light generation, that is also ultra-fast switching of classical optical signals, that is all optical quantum simulation, and also extension of coherence time in the system. Okay, so these systems, both Tavis-Cummings and Tavis-Cummings models, were studied experimentally in atomic systems, quantum dot systems, as well as in the superconducting systems and rare earth ions. And the applications were in the quantum communication, quantum memories, quantum simulation, and more. Now, there are interesting differences in physics between these 2 models. So here we are looking at what happens if we have an excited atom and we let it evolve in time. In the case of the Tavis-Cummings model, we see the Rabi oscillation. So basically our atom starts excited and then it exchanges energy with a cavity coherently, but the cavity is lossy, so we slowly lose that amplitude, and eventually the excitation is fully lost to the environment. In contrary, if we have, in this case, 11 atoms in a cavity, and I'm looking into the Tavis-Cummings model, what we see first is that the atom has Rabi oscillations, but they are more frequent. And that is because light and matter interaction is higher. The exchange is not only with the cavity, it is also with the other atoms in the system. Because of that, because of the role of subradiant states in this process, what happens is that the excitation is not fully lost to the environment. In addition to these time evolution details, we have also explored how Tavis-Cummings model can be beneficial for quantum light generation. So here I'll talk a little bit about the photon blockade effect, which is a standard way of generating single photons in a cavity QED process. So what happens is that our cavity with the emitter behaves as a filter of laser light into the single photon source. So basically it's changing Poissonian statistics into the single photon statistic. However, it's not perfect. Sometimes it gives us 2 photons. And so to understand why, we look into the underlying mechanism. The typical thing about the Tavis-Cummings Hamiltonian is that it creates an harmonic ladder. That means that in the first excited state, we'll have 2 polaritons, and then in the second excited state, those the next 2 polaritons will not be double the value of the first 2. So if we target the system with the energy of the upper polariton, and the system absorbs the first photon, the second photon will not be absorbed because there is no energy level there because of that unharmonicity. So similarly, if we have 2 atoms in a cavity, and in this case, it's a non-resonant case, so neither the atoms nor the cavity are resonant to one another. What happens is now we don't have just 2, we have 3 states in the first excited rung and 4 states in the second excited rung. And so in addition to the same way, to the polaritonic photon blockade that we had in the case of the Tavis-Cummings Hamiltonian, now we have another way of generating single photons, and that is by using this subradiant state here, the 3rd state that occurred as we added new atoms, and the little windows that open up in the second manifold, second excited manifold. And so what happens here is that we get higher purity of single photon generation. So if you compare between these 2 illustrations, you'll see we have mostly single photons, whereas in the previous cases, they were mixed with the 2 photons. And so this shows that on the practical terms, Tavis-Cummings Hamiltonian is of interest for building quantum hardware for quantum communication and other applications. However, modeling Tavis-Cummings Hamiltonian is computationally very expensive. The exact approach, which is the quantum master equation, which solves the Lindblad dissipator, and usually this is implemented using Qtip, which is the quantum toolbox in Python. This method requires exponential memory and runtime. And so it usually limits us to studying only a handful or a little bit more, so a single-digit number of emitters in a cavity. Then we sometimes use the approximate methods, such as effective Hamiltonian and scattering matrix, which have polynomial scaling, and they're applied for low excitation cases, which are usually the reflection of our experimental reality. So having 1 or 2 excitations in the system is enough to study these effects for the hardware we are making. If you're interested in more details about this research, you can see some of our prior papers. But another trend in modeling open quantum systems has emerged in past few years. Modeling open quantum systems on NISQ hardware has been pursued by several different groups, including Sabra Kais and Narang group and Mazziotti group and others. But we were especially inspired by this paper by Garcia Perez and collaborators that model the Tavis-Cummings open quantum system on an IBM quantum computer. So Tavis-Cummings system has only 1 emitter and 1 cavity. And we were wondering whether this problem can be generalized to the Tavis-Cummings model. Clearly, it's a more complex problem. There are many more dimensions in the Hilbert space, but this is the problem that we decided to solve, and this was done in the collaboration with Professor Marina Radulaski from ETH Zurich. So the first thing we started thinking about is there an intuitive mapping between the Tavis-Cummings model and a quantum circuit? And that is because atoms are two-level systems and qubits are two-level systems too. So if we just look at the atoms and we look at one excitation, it can be represented as a superposition of singly excited qubits in the system. And for us to study what happens in hardware, we want to see what is happening to these amplitudes that come with the individual singly excited states. So to solve that, I will dedicate several slides to theory. If you don't like derivations, just bear with me. We'll go back to plots in about 4 to 5 slides. But let me first give you a map of how we tackle this problem. So we started with a model and atoms in a cavity. We wrote a Hamiltonian and turned it into interaction picture. Then we limited ourselves to single excitations and solved the Schrodinger equation. And then we traced out the environment and used Laplace transform. And finally, we calculated the system density matrix and mapped it to a quantum circuit. So in the end, we have a quantum circuit that maps the interaction of n atoms in a cavity in an intuitive way. So let's start with the first step. So we first write down the Hamiltonian. The system Hamiltonian is a collective excitation of n two-level systems, and it can be represented through the collective spin operator SC. And the environment is represented as a set of bosonic modes. The interaction is given by the Tavis-Cummings Hamiltonian, which is excitation preserving. So it models the exchange of the photon between the bosonic mode of the environment with one of the emitters in the system. And these bosonic modes will later be converted into a Lorentzian cavity that is coupled to atoms.
How robust is the theory to imperfections? In the sense that, sure, you can have SC for the total spin of the system, but in real life, the qubits will probably have different frequencies each.
Mm-hmm. Yeah, that is an excellent question. And that is a problem that we're currently tackling. So I do not have results on it, but this is our first result. We start with just the basic system, which already has some complexity of what we want to study, such as Rabi oscillations and the loss of the amplitude. So yeah, I agree with you that ideally what we are building toward is having these emitters non-identical. That is the model that we studied past 5 years with effective Hamiltonian approach. We have a lot of conclusions from that. One that I showed was the photonic blockade becomes better in the Tavis-Cummings model. But yeah, at the moment, I can guide you only through the resonant case.
Okay.
Yeah, if there are any more questions, feel free to jump in. It makes the presentation fun. Okay, so in our next step, we want to convert the interaction Hamiltonian into the interaction picture by sandwiching it with these exponents. And ideally, we want to get to this form where we have the same form of the Hamiltonian, just all of our operators have the time dependence. And so for the B operators, that is easy because it's pretty simple to show that they will have exponential time dependence. But for the raising and lowering operators of our two-level systems, it is not trivial. And on the next slide, I will show you how we tackle that. But I will just now show you that we have that in the end, we come down to the same elegant exponential dependence in time. Okay, so to derive this, we first need to notice that as a z is a diagonal operator. If that's so, that means that its exponent is also going to be diagonal operator. And the elements on the diagonal, we mark them as xp. And then we notice that xp can be expressed through n and the Hamming weight. Hamming weight, for those who don't know, is a bit sum in the binary representation of a number. So for example, number 5 in the bit representation is 101. And if you sum that up, 1 plus 0 plus 1, its Hamming weight is going to be 2. And so with this function, we can then simplify our calculations, and it cancels out nicely. And so in the end, we can get this nice exponential dependence. However, these XP terms will also prove very useful in Schrodinger equation solving. Those details you can check on arXiv. I believe our preprint is going to be online tomorrow. We've just submitted it with all the details of the calculation. For the next step, we'll limit our system to up to 1 excitation, which means that our wave function is a sum of vacuum, singly excited atoms. And if you remember, these amplitudes are what we want to study, how our system evolves in time, and singly excited bosonic modes of the environment. Then we solve the Schrodinger equation, which gives us a relationship between these different amplitudes of atomic excitations. And here we also have this function J of omega, which is the density of states of the environment. And this is exactly where we place our open quantum system condition. So if the environment is just the cavity, then our Lorentzian dependence will just be a delta function. Our line width of the Lorentzian will be kappa. And if our cavity is lossy to the environment, then it will have some non-zero kappa. And so kappa is the loss rate of the cavity to the environment. And so our density of states is a multiplication of the Lorentzian of the cavity with the square of the coupling rate of the atoms and the cavity. So now with that, we move on to trace out the environment, which then gives us the n+1 times n+1 density matrix, which has diagonal terms that are giving us population of atoms. So basically their excitation amplitude squared. While the last element of the diagonal is the combination of the cavity and the environment. And we solve using Laplace transform, we solve for these terms, and they are dependent on n, g, and kappa. So the number of emitters in the cavity, their coupling to the cavity, and the loss of the cavity. Okay. So now in the next step, we devise a quantum circuit that will map our dynamics of the Tavis-Cummings dynamics onto n+1 qubits. And so we named this quantum mapping algorithm of resonator interaction with n atoms.
In the previous slide, aren't you in the small kappa limit? Isn't the imaginary?
Yes, it can be imaginary, but that comes here into Cinch, and it
Okay.
doesn't, and then you put it into the module squared, so it doesn't matter in the end.
Yeah,
we get
I just want to know if those terms were oscillatory.
Mm-hmm. Yeah, so the thing is that if G is small, this will be positive, and then it will have damped oscillation. And if G is large, then this will be imaginary, and we will have Rabi oscillations, as we'll see on the slides that are coming up. Thank you. All right, so yeah, so then in the next step, we map that onto a quantum circuit, which we named the quantum mapping algorithm of resonator interaction with n atoms, which has a really nice abbreviation, Q-MARINA, that matches the first names of both myself and my collaborator, Professor Marinkovic. In addition to having fun with quantum photonics, we were also having fun with the naming of the algorithm, but let's see what it actually does. Okay, so we have n+1 qubits. The first n qubits represent n atoms, and the last one represents the lossy cavity. So basically, whether photon is in the cavity or in the environment, it will be combined in this last qubit. Then we make the first atom excited by using X gate, and then we continue coupling each atom with the environment using a pair of entangling gates. So the first gate is the CU3 gate with parameters theta, These parameters are a function of the system parameters G, kappa, and T. And then the C naught is just the C naught. What you can also notice as a detail of this circuit is that the first two entangling gates have one orientation, and then all others have the opposite orientation. The nice thing about the circuit is that it's linear in both space and time. In space, it uses n+1 qubits, and in time, it uses 2n entangling qubits. So now, starting with the exact solution, which requires exponential space and time, we have reduced the complexity to the linear space and time. Let's see how this algorithm works for the simple case of two atoms in a cavity. Okay, so the idea of the algorithm is to limit the wave function to the superposition of singly excited states. So in the first step, we apply the X gate and move straight into 1, 0, 0 state where the first atom is excited. Then by using pairs of entangling gates, CU3 and CX, we maintain the wave function within these orange states that are singly excited. And again, after these two states, after these two gates, we also end up in a superposition of the environment, the second and the first atom excitations. And we set it up so that these amplitudes match the amplitudes of the first and the second atom. And that is how we achieve this quantum mapping. So if we run the algorithm and measure the probability of state B of the first qubit being excited or the second qubit being excited, that will give us the probability that the first atom is excited or that the second atom is excited. Let's see how that works. So here's an exact solution using the quantum master equation for 7 atoms in a cavity. So here's our first atom that has the Rabi oscillations, and the second atom that, or rather, these are all atoms from 2nd to 7th. They look the same. They have the same dependence. They have Rabi oscillations in the opposite phase. And we simulate our algorithm with 40,000 shots in Kiskit-Kazan environment. And what we see is that we have matching oscillations and matching intensities. We can also see that there is some noise, which is occurs because we have a limited number of shots. Now, next thing is to look at the scaling of our approach. So here we compare the quantum master equation, which takes exponential runtime as a function of the number of atoms in the system, whereas our quantum algorithm is linear in the number of emitters. In terms of the space, the same story. The standard exact quantum master equation solution is exponential, while our quantum approach is linear. Here we zoom in to just be able to see that linearity compared to this exponential growth. So now let's think about how we can implement this quantum algorithm on actual quantum hardware. So for that, one of the main considerations is the connectivity. And so if we look at this connectivity of the algorithm, each system qubit couples to the environment qubit, but not among themselves. And this is analogous to what happens in the Tavis-Cummings model, where each atom couples to the cavity mode, but not to one another. So for that, when we map from here to there, we see that we have star connectivity, where in the center we have the environment qubit, and then all system qubits are connected to it. So if we are to use some of the commercial hardware, such as IBM and IBM Q, which we actually have access to at the moment, we can simulate either 2 or 3 atoms in a cavity with a star connectivity. On IBM Q, which has all-to-all connectivity of 11 qubits, we could go up to 10 atoms in a cavity. Now, of course, this is not an exhaustive list of systems. Of course, there is Advanced Quantum Testbed with all-to-all connected chips, as well as the Sandia platform with trapped ions. So there are other venues that we expect to test our algorithm on. But for now, let's see what we obtained on the IBM quantum computers. This is executed on IBM Q system, where we use these two atoms connected to this one cavity environment qubit. And the dots represent the experiment data, while the solid lines and dashed lines represent the quantum master equation solution. So what we see is that we have a pretty good match in terms of the oscillations. The gray line, the data for the second atom match a bit better than for the first atom. What we see for the first atom is that we get this systematic drop in the overall amplitude, but the pattern is maintained. So we have the oscillations at the right frequency. We're still trying to understand why this is so. If you have any ideas, please shoot, because we think that it could be the device or qubit dependent. Now, when we go to the next, a little bit larger system with 3 emitters in a cavity, for which we use IBM Oslo system, we get a bit better match. And so we see that the atom 1 matches well, apart for these few runaway data points. And then we can test how the atoms 2 and 3 behave, because they should have the same behavior against the exact solution. And we see that they, again, follow the trend very well, but there's a little bit of drop in the overall amplitude. And so with that, we have tested our algorithm that shows that NISQ computers can model open quantum system cavity QED effects. Now, we have many ideas in where to take this research, and we are also open to your ideas and suggestions. Some of the systems that we would care about, as actually David mentioned already, are the non-identical atoms. We are also interested in growing the number of emitters in the system. And so for that, we will be checking out some of the other hardware. Now there, in addition to the connectivity, the depth of the circuit will be competing with the coherence time. So we expect that the performance of our algorithm will become only better as the bigger and more reliable systems are built. But the promise of this approach is that with just a handful of qubits, we can already simulate some of the exponentially hard problems with a quantum master equation. Of course, I should mention this is not a quantum advantage of any sort. It is really our approximation of the problem to only important details such as the single excitation and so on. Another direction we're interested in is to simulate this with 2 excitations and expanding to other types of Hamiltonians other than the Tavis-Cummings. And so with that, I have presented you the first result in our line of research to use the available NISQ quantum computers to model photonic physics in nanophotonic systems, where we have hybridization of light and matter, and understand the underlying physics, which helps us design better quantum hardware, which we do in our experiments. And with that, I would like to acknowledge my team at UC Davis, especially Victoria Norman and Tristan Adams, who work on this project. I would like to thank my collaborators, especially Professor Marina Radulaski, who we are working closely on with this research. We would like to thank our funding sources. If you're interested in discussing or collaborating, you can find us at these coordinates. We're always open for conversation. Thank you.
Thank you, Marina. Are there any questions, comments from the group?
Hello.
Hi.
My name is Jan. I enjoy your talk. I have 2 suggestions for your execution of the circuit on real hardware. So I don't know if you mentioned this, but if you would do readout correction for your measurement on IBM Q, you will get better results.
Thank you very much. We have not tried it yet. Thank you.
It always helps, but I have a much better suggestion. For the most of the IBM Q devices, the typical practical circuit depth is around 10 CNOT gates. If the circuit is longer, you just get very bad results. However, we have access to a different technology, trapped ion. They offer two advantages. The circuit depth can be around 60 in the CNOT gate. So you can run way larger circuit, but more importantly, they offer all-to-all connectivity. So you are not anymore limited to this daisy chain connectivity which you have on IBM, which at the end translates to much longer circuit, because you need to do many swaps for if you have more than 3 qubits in your circuit. On the trapped ion, you can get up to 20 qubits. So it is just different level of technology.
Thank you very much. That one actually we did think about. Yeah, I understand everything that you've suggested. We've been working with Ion Q on a project, and so far, we're not yet at the stage to present those results, but we are seeing good results up to 5 emitters, and then for above 5, we need to also do some tinkering to probably maybe relating to your first suggestion to do the readout correction, because we are getting correct shapes, but not necessarily the amplitudes of the evolution of atoms. So where do you have access to 20 trapped ions?
It is through Oak Ridge.
Oak Ridge,
One Quantinuum is the hardware. So if you have access to Oak Ridge, you can request access to Quantinuum.
Wonderful, thank you.
This is a Honeywell hardware device.
Yeah, I know they're doing great. Yeah. Thank you very much, Jan.
You're welcome.
Any other questions or comments? So then let's thank Marina again. Thank you very much, Marina. It was a really good talk.
Thank you. It was fun to be here.
And thank you everyone for attending.